Hey everyone, I'm Jigyasa Grover and I work as a machine learning engineer in the ads prediction team at Twitter. Today we will be talking about how we can fuel our machine learning models via feature engineering. The last couple of years have seen an immense growth of machine learning in multiple domains, from influencing our shopping lists to cars self-driving themselves around the town. Unquestionably, machine learning is the most used and abused subdomain of artificial intelligence presently. It is being wielded in improving healthcare and advancing warfare, in scrutinizing your resume to determining your creditworthiness, in creating music with meaningful lyrics to synthesizing pictures and videos of people non existent, and so many others. Regardless of our fascination or loath for it, it is influencing our decision making power and is dominating our lives heavily. To describe machine learning and is enabling computers to learn on their own. The power of spotting patterns on their own without the requirement of programming is the biggest edge these decision making systems have over the others. Researchers keep traversing unexplored territories of machine learning, whereas, according to experts, the businesses have just seen the tip of the iceberg. According to the Finances Online, 28.5 billion US dollars were allocated to machine learning in just the first quarter of 2019, and it is expected to grow to 40 billion US dollars by the end of 2025, from starting at 1.3 billion US dollars in 2016. Almost 50% of the companies have either been exploring or planning to do machine learning in near future. The number of startups focused on purely ML have seen a 14 times rate of increase currently. 97% of mobile users use machine learning trained voice assistants, with a 40% of search just powered by voice. Advancement in the software aspect has also led to a projected growth of 120 billion US dollars global sales of AI powered hardware by the end of 2025. Enterprise domains like security, analytics, sales, and marketing are reaching new heights with machine learning adoption of 25%, 33%, and 16% increase rates, respectively. Dominant leaves are leaving the scientists, investors, policymakers, business leaders, and the audience bedazzled, hinting that human like intelligence in machines might be just around the corner. Nonetheless, the progress in machine learning has been impressive, but there's a lot of pending explanation and examination, which keeps the research going on. For the state of the art learning algorithms to work their magic on, it's important to focus on the three key dimensions: data, algorithms, and computation. The strong build of learning algorithms comes from the iterative process of validating hypotheses through experimentation, whereas the computation comes from optimizing the learning algorithm using distributed computing to run at large scale. However, laying the foundation of the process with perfect quality and quantity of data is the secret sauce of creating a successful machine learning model. Since we have progressed from the rule-based approach to a more data-driven approach, it goes without saying that machine learning algorithms are trained to capture implicit information from the data provided. It is true that these approaches are very, very data hungry. Without going into many details, deep learning algorithms or neural networks have many parameters that need to be tuned, and therefore a lot of data needs to go inside it in order to come up with a more generalizable model. So in that sense, having a lot of data is the key to coming up with good training sets for those approaches. The type of data fed into the algorithm has profound effect on the success of the algorithm. Worthy data collection forms the foundation of the pyramid of the AI hierarchy of needs, drawn parallel to the Maslow's hierarchy of human needs by Monica Rogati, a renowned data scientist and an AI advisor. She puts forward that data literacy, collection, and data flow forms the basic needs which must be satisfied to achieve ultimate nirvana, which in our case would be the attainment of artificial intelligence. There might be a few additional steps in the pipeline before we can use the data as it is in a machine learning model. These values, easily understood by humans, but an ML algorithm might have trouble learning from the type of data and it might need some encoding to work. Let us just consider the simple image on your screen. It is a 350 into 350 image of pixels, and it's an image of yin and yang. We can obviously understand by just looking at it, but a machine would not. For the machine to understand it, as we said, we need to encode it. And here, just as an example, we would be using vectorization. This mandatory transformation involves converting all kinds of non-numeric data, be it textual, graphical, or categorical, into numeric form, as numbers are the only thing that the machine understands. Learning algorithms require graphical data, and that's why you can convert that yin and yang image of 350 into 350 into a 2D array if the image was simple grayscale. And thus you can say the process of transforming raw data like an image to a set of quantifiable values like an array of numbers is called feature engineering. And what a feature is, it's an attribute or a property shared by all the independent units or the training examples on which the prediction is to be actually done. Feature engineering is one of the key techniques that often does not get its due limelight. Much of the success of machine learning actually is a success in engineering features that the modeler or the learner can understand. And this is where the intuition comes into play. This is where creativity and black art comes into play. This step is actually more important than modeling because ML algorithm learns from what data we give in, garbage out. And thus choosing right features in the right format can boost the performance of a simple model by far. It increases the transparency of the model. You get to know what goes in, how it works. It reduces the need to do heavy ensemble learning or combining different kinds of models. It also reduces the need for tuning different parameters involved in a model. But there's an interesting fact that should actually be put forward, despite this being very important, more important than machine learning training itself or the modeling itself. Forbes recently published a new survey in which they found that data scientists spend most of their time massaging the data rather than mining or modeling it. It was found that data scientists spend 60% of their time on cleaning and organizing data. Collecting data sets comes second at 19% of their time, meaning data scientists spend around 80% of their time on preparing and managing data for analysis. 76% of data scientists view data preparation as the least enjoyable part of the work, which can be, a red signal. But why is that people don't like it? Because the process is such. But we should figure out what is the actual process that goes behind feature engineering. This step is more important than the actual ML modeling as we learned. The first would be analyzing the trends, researching the domain, and coming up with ideas, talking to data scientists, talking to domain experts, discussing with people and brainstorming. And then you would do like a quick offline transformation and perform statistical analysis on the data that you already have. You would test it with existing model present offline and not going into production directly. But if it doesn't work, you have to go back to the brainstorming stage and try improving the idea. If the idea works, then you work on getting it productionized, integrating it in your online pipeline. You run it online, see the results, serve it, and continue the process. And hence, applied machine learning is what basically feature engineering is. The critically acclaimed Andrew Ng says, coming up with features is difficult, time-consuming, and requires expert knowledge. And feature engineering itself is a subdomain of applied machine learning. But now that we've understood what feature engineering is, it is also very important to draw boundaries and understand what exactly is not feature engineering. So initial data scraping or collection, creating the label or the target, data cleaning, removing duplicates, handling missing values, imputations, scaling, normalization, all these terms do not count as feature engineering tasks. So by now you must have understood that if data is the crude oil, what you extract from it, the features, is the actual fuel we need. So let us quickly go over the different techniques of feature engineering that might come in handy. Let us assume we have like an app store preview and you want to extract data from it. So just in like a simple JSON format or even in a simple dictionary format, let's just say you've extracted the value. The app store is iOS App Store. The category of the app is social. The languages the app is present is English, Chinese, Hindi, French. And the age of the app is like 1350 days. The rating of the app is 4.7 out of 5 stars, as mentioned on the App Store preview. But it is just assume that this data is something like the attributes that would help you, make an app recommender system for someone. But it should be kept in mind that these features or these attributes cannot be directly input into the model because, as we talked about, the model only understand numbers. So we would, make features out of them. So how would we do it? Let's take the first one, App Store. You can say the App Store is iOS App Store. But there could be other app stores as well, like be Google Play Store or, Amazon App Store and stuff like that. Or there could be other operating systems that could come up. So you always have to keep a buffer. You could do a one hot encoding. That means you'll always just like light up one of them. So let's say App Store is 100. Similarly, app category, you can do like travel, social, business, productivity, etc. But the point to be noted here is the same very app could be belonging to different categories. It could be a travel and a social app. So you have to make sure that your provisions are such, and that's why you could use something like multi-hot encoding. The same goes with app languages because the same app can be present in different languages. Hence, let's say you have like English, Hindi, French, and so on. The app age days you can leave as it is because it's a number, and same goes with app rating. Of course, you can make multiple features, but what makes them worthwhile, which gives them the maximum signal, it's important to know what actually makes a good feature in that case. Let's talk about different cases. The first is good feature should always appear more than 5 times. That is, it shouldn't be an outlier. It shouldn't be like a rarely occurring entity. By this, it provides a differentiating power. And instead of being a minority, it does not allow the majority to overshadow its power. And it does not become an anomaly instead of a feature. The second could be to give the feature names precise and clear meanings. For example, app age as a feature name could be very confusing. Is the app age in days, in seconds, in milliseconds, in years? How does it go about? So app age days could be a nice way to name a feature. The number of days the app is old. Another interesting point to note is let's consider the app rating feature. We all know as humans that the app ratings can only be between 0 and 5, the number of average stars it gets. But the machine won't. It could even count like -1 as a feature value, which it should flag or not train on. Thus, you should explicitly mark these values or remove them from your data set. The best way would be to mark these magic values by a Boolean flag. Is app rating defined, like correctly defined? And then so on, the machine learning model could train on. And another interesting fact that you should maybe consider is avoid mapping values like string values to maintain stability. For example, assume that the app language is English and you use an external source which maps English to the, say, number 24. And you use the number 24 in your machine learning model. Let's say after a couple of years, new languages come up and the ordering gets changed. Language English is not mapped to 24 anymore. It gets mapped to, say, 8. Your model won't know because your mapping was based on an external source. Hence, it's always better to not map it, instead encode it. So relationships matter. This holds true in all personal and professional worlds, and so it goes true for machine learning models and features as well. Let us look at this graph. It just maps app price, app languages, and app ratings. If you see, as the app price goes down, you see the app rating increases. This is just a trend that you see visually. But if you see at app languages, the number of app languages go up and down. they're not affecting app price, app rating. This is just like a general view. We will shortly be coming back to this. But before that, we should understand how relationships between multiple attributes or features can be formed. And understanding these relationships is what comprises feature correlation. Feature correlation is an important study. It leads to useful insights like how the attributes depend on each other. Are they causes of each other? Or they're associated with other features as well. Correlation study helps in predicting one attribute from other. It's also a great way to impute missing values. It also sometimes indicates the presence of a causal relationship. So coming back to this graph, as we talked about, app price decreases and app rating increases. That means they have a positive correlation. So, sorry, a negative correlation. But if it would have been the case that app price decreases and the number of app installs also decreases, it would have been a positive correlation because the decrease in one also causes the decrease in other, whereas the increase in one would also cause an increase in other. However, it's not the case to always have a correlation. There could be no relationship between these attributes as well. So mostly we study three different types of correlations: positive, negative, and then none. By now, we all have understood how features enable models to learn, but not all features assist in the same manner. Talking about quantity, if I may, that is when feature importance comes into play. It explains the predictive power of the features in the training set, and it forms a critical part of machine learning interpretability and explainability. One of the most common ways is to calculate feature importance via randomized decision trees. It just averages the estimates of predictive ability over several random decision trees. Not going into depth of it, but it just gives the result something like higher the score, the more important the feature is. For example, if I ran the feature importance um, methodology on my data set, I found that number of app languages is the most important feature, and that's what determines the highest predictive power of that feature. And this process of selecting a subset of features is very important because, as you know, the number of features increase, it could cause issues. And that's why we need to be very selective about our process. We aim at selecting features that can make predictable variable more accurate, and we try to remove irrelevant attributes that might actually be just getting noise into our model. It leads to simplification of the models. It is easier to interpret because the smaller number of features that we have without affecting the model performance, it is better for us to understand and also for the model to train easily and faster. It protects us from curse of dimensionality. And what is curse of dimensionality, you ask? It just is bloating up the feature space. If you use too many encodings and embeddings, if you saw in previous, just encoding the app store bloated the space, and it makes the model harder to cluster and causes every observation to appear equidistant from others. Therefore, it just bloats up the feature space, and it's very difficult for the model to generalize. And this is also known as feature explosion. It leads to a quick growth in the total number of features. Feature explosion can be stopped by different techniques, and especially by feature selection, where you are very selective, eliminate unnecessary features, and it can take on many forms. By now, we have touched so many different topics in such a short amount of time, and you must have comprehended by now that feature engineering is an exhaustive process. And doing it daily makes it, with tons of data, is all the more cumbersome. And data scientists and machine learning engineers often don't find this data massaging job to be as exciting. Typically, feature engineering is a drawn out manual process based on domain knowledge, intuition, and data manipulation. And it can be extremely tedious, and the final features are obviously limited by human subjectivity, our own intuition, our biases, and time. And thus, it's when automated feature engineering comes into play to help us. It's an automated process, as you guess by the name, to create as many candidate features as possible out of a data set, and from which we can use the feature selection techniques to find the very best. Feature Tools is an open source tool by Python for doing automated feature engineering. Pedro Domingos, in his critically acclaimed article, says one of the holy grails of machine learning is to automate more and more of the feature engineering process. to conclude, I would say good and reliable feature engineering is like a strong foundation for machine learning modeling. And more data can beat clever algorithms, but better data beats more data. Thank you so much. And it was a pleasure to meet all of you. Hope to connect with you sometime soon. Thank you.